Imagine this, two black holes, each dozens of times more massive than our sun, spiraling toward each other at nearly half the speed of light. In their final moments, they collide with such force that they send ripples, literal distortions, through the very fabric of space and time. These ripples, invisible to the naked eye, traveled over 1 billion years to reach us. And on September 14th, 2015, we finally heard them, not with our ears, but with the most precise instruments humanity has ever built. Gravitational waves were first predicted by Albert Einstein in 1916 as a consequence of his groundbreaking theory of general relativity. Einstein described space and time as a unified fabric, something that could be stretched, bent, or even twisted by a massive object. He believed that when massive objects accelerated, such as two orbiting black holes, they would send ripples through space-time, just like a stone dropped in water. But there was a catch. Einstein himself doubted we would ever detect them. For decades, gravitational waves remained a fascinating yet unproven idea. Scientists debated their existence. Theorists questioned whether they could even be measured. The waves were real, but detecting them, that was a challenge beyond the limits of technology for most of the 20th century. Then, in the 1960s, a physicist named Joseph Weber built what he claimed was the first gravitational wave detector, a massive aluminum cylinder designed to ring when waves passed through it. But the scientific community remained skeptical. Weber's results were never conclusively verified. Fast forward to the 21st century, with technological advancements, a bold new approach was taken. Instead of just using a giant metal bar, scientists constructed the Laser Interferometer Gravitational Wave Observatory, LIGO. Two massive L-shaped observatories, one in Washington, the other in Louisiana, designed to detect space-time ripples smaller than a fraction of a proton. The concept: shoot lasers down two perpendicular tunnels, each 4 kilometers long, and measure if gravitational waves distort the light's path. The precision, 1,000 times smaller than an atomic nucleus. And then it happened. A tiny disturbance in the fabric of reality. A signal so faint yet so distinct. A chirp in the data, exactly as Einstein predicted. The source: two black holes merging, 1.3 billion light years away. In that fraction of a second, more energy was released than in all the stars of the visible universe combined. Humanity had, for the first time, heard the universe in a brand new way. It was a Nobel Prize-winning discovery. But how do we even detect such tiny distortions in space-time? The secret lies in interferometry, a method where we split a laser beam, bounce it off mirrors, and then recombine it. If no gravitational wave passes, the beams cancel out perfectly. But if space-time stretches or compresses, even slightly, the beams fall out of sync, revealing the presence and magnitude of a gravitational wave. Gravitational wave astronomy is only beginning. Future observatories like LISA, a space-based interferometer, will allow us to listen to the universe with even greater clarity. We may one day detect primordial gravitational waves, ripples from the birth of the universe itself, or new exotic objects like boson stars, or even cosmic strings. We used to think the cosmos was silent, that space was an empty void, but we now know it is alive, with sound, a cosmic symphony of space-time itself. With each new detection, we are not just confirming Einstein's theories, we are expanding the frontier of human knowledge. And who knows, the next great discovery, it may be just a ripple away. Thanks for watching. And if you enjoyed this kind of content, please consider subscribing. We're just getting started, and we're really excited about what we have planned for the future. You won't want to miss it. Finally, just take a moment as you go about your busy day, and remember, there's a whole universe out there just waiting for you to explore it.